my name is Michael Pendazis. This is Math 231 Linear Algebra homework problems for test number 2. I'm going to be going over homework problems that from 3.1 to 3.5 and 4.1 to 4.2. This is in addition to the lectures I'm posting on YouTube, and so this is just for you to check your answers, the homework problems, and to help you study for the second exam. Okay, so let's get started. Okay, so I'm going to be following the homework sheet problems. So in 3.1, the problems are numbers 11 and 15. So let's start with that section. So number 11 in 3.1. So I'm going to assume you have the textbook in front of you and that you can look at the problem at home. So number 11 in 3.1, okay? So for number 11, let's put down the important information. The vector u is the vector -3, 1, 2. And v is the vector 4, -3, 2, -3, 2, 1, 0. And v is 4, 7, -3, 2. W is the vector 5, -2, 8, 1. Okay, so this is u, v, and w in the problem. And so in 11, we have to find the components of each vector, right? So the problem is find the components of. And so in part A, the vector we want to find the components of is the vector v minus w. Okay, so v minus w is just the vector v there minus w. Okay, and so if you subtract the corresponding components, 4 minus 5 is -1, 7 minus -2 is 9, -3 minus 8 is -11, and 2 minus 1 is 1. Okay, so that's A. Negative u plus v minus 4w. Good. So negative u is negative that vector plus v minus 4w. And so v is here minus 4 times w. And w is here. Okay, so it's negative u plus v minus 4w. And so if you do the arithmetic here, you're going to get 3, -2, -1, 0, plus, I'm going to do the arithmetic here. So it's going to be 4 minus 4 times 5, that's 4 minus 20, which is -16. 7 minus 4 times -2, that's 7 plus 8, which is 15. -3 minus 8 is -11. And then 2 minus 1 is, sorry. 4 minus 20 is -16. 7 plus 8 is 15, that's fine. -4 times 8 is -32. -3 minus 32 is -35. Yeah, it's -35. And then 2 plus minus 4 is -2. So that's what goes in the bracket there. So I'm just going to check. 4 minus 20 is -16. 7 plus 8 is 15. -3 minus 32 is -35. 2 minus 1 is, 2 minus 4 is -2. Good. Okay, so you just add those two vectors and you get -13, -13, -36, -2. Okay, and so negative u plus v minus 4w is that vector. And the other problem in part A, that was the answer. Okay, -20, -16, 7 plus 8 is 15, -3, -32, -35, 2 minus 4 is -2. Good, okay, so that's A and B, and then the other parts are just very similar. And so let's go to number 15. Okay, so the next problem in 3.1 is number 15. Okay, the components of a vector, right, are just the first, second, and third and fourth components of those vectors I wrote over there. Okay, 15. You're given this vector u, which is the vector negative 2, 1, 0, 3, 5, 1. So negative 2, comma 1, comma 0, 3, 5, 1. So that's u, and then we have to determine which of the following vectors in R6 are parallel to that vector. So in A, the question is the vector in part A parallel to this vector? Okay, so the question is this vector parallel to that vector, right? And so two vectors are parallel, right? If they're parallel, they have the same direction. They don't need the same magnitude, but they need the same direction. And if they have the same direction, that's equivalent to saying that one vector is a constant multiple times the other vector. And so it's showing that u and v are parallel, or parallel is equivalent to finding whether or not one is a constant multiple times the other. Okay? So in order for this vector to be a constant multiple of this one, we need to go from negative 2 to 4. We need to multiply u by negative 2 to get this vector, right? And so if negative 2 times negative 2 is 4, 2 times negative 2 is negative 2. And this would not work, right? And so this is not a scalar multiple of that vector. This is false. And so because this is false, it's also false that those two are parallel. So this is not parallel, since it is not a scalar multiple of u. Okay, so since this vector is not a scalar multiple of u, it's not parallel to u. Okay, and so the other one's very similar. I'll just point out. Let's see, part C is just sort of a weird example, so I'll include this. This is the sixth tuple of all zeros. This is the zero vector in R6. So is this a scalar multiple of u? And the answer is yes. Let's call this 0 in R6. 0, the zero vector, is equal to 0 times u. So the zero vector is a scalar multiple of that u. And because it's a and because now this is true, it's true that they're collinear. The zero vector is actually it's actually parallel to any vector, because you can assign the zero vector any direction you want. And so the zero vector actually has an arbitrary direction. It doesn't have every direction. It has one direction, but you can choose that direction arbitrarily. And so by choosing the appropriate direction for the zero vector, you can make it parallel to that u. Okay, and so because 0 is a scalar multiple of u there, that's true also, right? This v is different. Okay, the idea that this zero vector is a scalar multiple of the other of u, and so it's true that they're parallel. So therefore, 0 and u are parallel. Okay. Since 0 is equal to 0u, that means the zero vector. This is the zero vector. This is the u vector. That's a constant. 0 is a scalar multiple of u, the scalar multiples each other, and so they're parallel. Okay. Okay, so that's part A and C for 15. B isn't much different from A. So that's section 3.1. Okay, 3.2. In 3.2, the problems are numbers 1 and 9. Okay, so for number 1 in 3.2, it's find the norm of v and a unit vector oppositely directed to v. And so for number 1, the vector in part A is v is equal to 2, 2, 2. We want the norm of v. Norm of v, right, is its length. So the norm of v is the square root of the sum of the squares of the components of the vector. And that's equal to the square root of 12, which is 2 root 3. So the norm of v is 2 root 3. Okay. Now, if you want to know a unit vector oppositely directed to v, it's a unit vector. So you want to know what the direction of v is. So if you think about you think about v dotted with itself, that would be the norm of v times norm of v times cosine of, okay, so we want to know what the norm of v is. So we basically just want to know what, so I want to let u equal to the unit vector in the direction of v. So u is going to be the unit vector in the direction of v. So u here is the unit vector in the direction of v. And so to find the unit vector in the direction of v, you just take v and divide it by its length. And then what you're doing is you're taking the vector v, you're getting rid of its length, in a sense. You're changing the length of the vector v from what it was to 1. And so it's going to stay the same direction, but it's now going to change to length 1. And so this is the unit vector in the direction of v. And so it's v divided by its length. And so it's the vector 2, 2, 2 divided by its length, which is 2 root 3. And that vector is 1 over root 3, comma 1 over root 3, comma 1 over root 3. Okay? You just take each component of v and divide it by the length of v, which is 2 root 3. So you get every component is 1 over root 3. And so if you want the unit vector in the opposite direction of v, just negate this vector. And so the answer is negative u, which is equal to negative 1 over root 3, comma negative 1 over root 3, comma negative 1 over root 3. That is the unit vector oppositely directed to v, the negative of the unit vector in the same direction as v. You get that. So that's the answer. Okay? And b is very similar. You just take another vector, you find its norm, you divide it by the vector by its length, or norm, and then you negate that, and you get the unit vector in the opposite direction of your original vector. Okay? So you follow these steps, and you can answer this problem. Okay, so that's one. That's number 1 in this section. And now we're going to go to number 9. Okay? And so for number 9, okay, so let's do part A. And so for A, u is equal to 3, 1, 4. V is equal to 2, 2, negative 4. Okay? And so the goal here is to find u dot v, u dot u, and v dot v. Okay, we want to find those two dot products. U dot v, u dot u, v dot v, giving you that u and that v. So u dot v is equal to, right, that vector dotted with that one, u dot v here, and you just add up the products of corresponding components. So 3 times 2 plus 1 times 2 plus 4 times negative 4. And when we do the arithmetic, you get 6 plus 2 minus 16, that's negative 8. Okay? Now if you do u dot u, that's 3, 1, 4, dotted with itself. Okay? And so you're just going to multiply corresponding components and add the products. And so this is 3 times 3 plus 1 times 1 plus 4 times 4. And that's equal to 9 plus 1 plus 16, which is 26. Okay? So u dot u is equal to 26. 2, 2, negative 4. Okay, so you're just dotting v with itself, and so you're multiplying the corresponding components, and then you're adding up the products. So this is equal to 4 plus 16, which is 24. Okay, and so these are the dot products of u dot v, u dot u, and v dot v. Okay, and so that's number 9, okay, part A. And the rest of it's very simple. So we're done with 3.2, and let's move on to 3.3. If you need to spend more time thinking about a problem, you can pause the video before I go to the next one. Okay. So the next section is 3.3. Okay, so 3.3 number 1. Okay? And you want to know in number 1 whether u and v are orthogonal vectors. Okay? So the question is, are u, v orthogonal? Right? That's the question. Right? And that's equivalent to asking the question, is u dot v equal to 0? Right? When two vectors are orthogonal or perpendicular, the dot product is 0. And so the question is whether or not the dot product of those two vectors is 0. And so for part A, we have the vector u is 6, 1, 4. So that's u and that's v, and we want to know whether or not they're orthogonal, you just check if the dot product is 0 or not. Okay, so u dot v is equal to this vector, 6 times 2 plus 1 times 0 plus 4 times negative 3. Okay, and so you multiply each of these products and you add up the products and you get 0. So u dot v is equal to 0. So because u dot v is equal to 0, the answer to this question is yes. U dot v is equal to 0. And so are u and v orthogonal? The answer is the same answer, yes. And so u and v are orthogonal. So therefore, that implies u and v are orthogonal. And so for the other parts of the same question, you can just check whether or not the two vectors, their dot product is 0. If their dot product is 0 using the Euclidean inner product, then they're orthogonal. If their dot product, then using the Euclidean inner product, if the dot product is non-zero, then they're non-orthogonal. Okay? And so that's 1, A, and the others are similar. Okay, so that's number 1. So next is number 4. Okay, so now number 4. So for number 4, here's the point P, and point P is 1, 1, 4. N is, okay, so that's a point P and that's a normal N, 198, just like in the book. And it says find a point normal form of the equation of the plane passing through P and having N as normal. Okay, so you can read the question in your book there. You want to find a point normal form of the equation of the plane passing through P and having N as normal. And so it's this. That is the point normal form of the equation of the plane passing through point P and having that as normal. Okay? The coefficients here, this 1, this 9, and this 8 are the corresponding components of N. 1, 9, 8. And the points, the coordinates of the point P, 1, 1, and 4 correspond with the x minus 1, the y minus 1, and z minus 4 there. And so that's how you write it. And so arbitrarily, if you have a point P naught of coordinates x naught, comma y naught, comma z naught, and a point and a normal vector n, a, b, c, then the equation of the plane passing through the point P naught and having normal n would be of the form a times x minus x naught plus b times y minus y naught plus c times z minus c naught is equal to 0. Okay? And so you can take this equation and you can just plug in a, b, and c here, and the x naught, y naught, z naught there. You can plug that into this equation, and you get that as the answer. Okay? That's the equation of the plane passing through that point and having that vector as normal. Okay, so that's section 3.3. So 3.4 numbers 11 and 19. So number 11. So for number 11, We have find the vector and parametric equations of the plane that contains the given point and is parallel to the two vectors. Okay, so the point in number 11, the point is the vector -1, 1, 4. And the vectors are v1, which is the vector 6, -1, 0, and the vector v2, which is equal to -1, 3, 1. Okay, so we want a plane that has this point on it and is parallel to those two vectors. Okay, let me just make sure that the parametric plane that contains point is parallel. Okay, so to do that, a general a general form of that equation would be if you start with the point, with this point, and you add a constant multiple times, let me put it this way, it's P naught plus C1 V1 plus C2 V2 is equal to your arbitrary point, P. So let me fill in everything here, and I'll maybe go into some more detail here what this means. -1, 3, 1, that's equal to x, y, z. Okay, so if you take P naught plus C1 V1 plus C2 V2, it's equal to an arbitrary point x, y, z. That's on the plane, right? What's happening in this picture is if you have the x-axis here, the y-axis here, and the z-axis here. If you have the point -1, 1, 4, like here, and you have this vector 6, -1, 0, that's your vector v1. And then you have the vector -1, 3, 1, like that. Then I'd say that's v2. This isn't drawn perfectly. So you have the point P naught there, and you have v1 here and v2 there. And so let's say you look at the plane. So we look at the plane going through those two vectors that those two vectors sit on. It goes through that point, right? There's our plane, right? The point P naught is there, and the vectors v1 and v2 sit on this plane, and the plane is going in all four directions, okay? And so if I wanted to talk about arbitrary point x, y, z sitting on that plane, then I could look at that point x, y, z on that plane. I could think of it as starting from the origin, by looking at point P naught, I'm starting from the origin, I'm going to the point P naught. And then to get to x, y, z, I can do that as a point on the plane because these two vectors are non-collinear. They're not multiples of each other. You can check that the only way, if I multiply this by -6, I get that. But if I multiply 3 by -6, that's not -18, right? So these are not collinear vectors because they're not scalar multiples of each other. That means as non-collinear vectors in R3, they determine one unique plane that goes through them. And so a point on that plane determined by those two vectors, you can think of that point as being the point P naught plus a constant multiple times 1 vector plus another multiple, constant multiple times the other. I would have to go some distance along V1 and then some distance along V2, starting at P naught, and I could end up at any point x, y, z on the plane. If a point was not on the plane, then if I went to P naught, which is on the plane, and I only traveled a certain distance along V1 and then a certain distance along V2, I could only go somewhere on the plane. I couldn't go anywhere off the plane. And so I could not get to any point off the plane by just starting at P naught on the plane and then adding constant multiples of vectors on the plane. I could only go to a point on the plane. I could also go to any point on the plane. And so by following this procedure, I can go to any point on the plane, but I cannot go to any point that is not on the plane. Okay, so I can characterize every point on the plane in this way. P naught plus C1 V1 plus C2 V2, where V1 and V2 are non-collinear vectors, and they determine one unique plane that goes through them. Okay, so we have this formula here. And so again, the question is find vector and parametric equations of the plane. Okay, so let's say I'm going to add up these three vectors, component by component. So the first component is going to be -1 plus 6c1 minus c2. The next component is going to be 1 minus c1 plus 3c2, comma 4 plus c2, and that's equal to x, y, z. Okay, so I just combined the three vectors on the left side. I multiplied this by c1, this by c2, kept that the same, added the three up, component by component. And it's equal to x, y, z, and so that means that this is x, this is y, and that's z. And so those are the parametric equations that determine a point on the plane. And so this is the vector equation. Let me point that out. This is the vector equation. Actually, you could say it. I guess you could call it the vector equation, but I'm going to call this the vector equation because there's a vector, there's a vector, there's a vector. So this is this is the vector equation I decided I'm going to use as the final answer. Vector equation. It's equivalent to that, but I'm going to say that's the vector equation. And then let's find the parametric equation by setting each of these components equal. And so okay, y is equal to okay, so those are the parametric equations that describe the plane, right? X is equal to this, y is equal to that, and z is equal to that. So these are the parametric equations, that's the vector equation. Okay? Okay, so that's number 11. Right? And if you try to think about this picture when you try to visualize what's happening in the problem and make sense of why this makes sense. Okay? Okay, number 19. So 3.4, number 19. Find the general solution to the linear system and confirm that the row vectors of the coefficient matrix are orthogonal to the solution vectors. Okay, so let me write down the system first. So it's x1 plus 5x2 plus x3 plus 2x4 minus x5 is equal to 0. x1 minus 2x2 minus x3 plus 3x4 plus 2x5 is equal to 0. So here's your system. Okay, so here's the system, and we want to find, again, the general solution of this linear system first. So our first goal is find the general solution. So find the general solution, and then there's other questions and we'll answer, other parts we'll answer that after. So find the general solution. First, let's think of the corresponding augmented matrix for this linear system. Okay. This is the corresponding augmented matrix for that linear system. And then I'm going to get this to reduced echelon form and use that to get the general solution. Okay, so linear system, augmented matrix, reduced echelon form. And so to get this to reduced echelon form, I'm going to take -1 times the first row and add to the second row. Okay, so -1 times the first row, add to the second one, and so 0, -7, -2, 1, 3. Okay, and so now I'm just going to multiply the second row by -1/7. I'm going to try to fit this in here. 0, 1, -1/7, -1/7, negative 1/7, okay? And so now I need a 0 here to get it to reduced to echelon form. The second row I'm going to keep the same. Oops, okay. Negative 1/7, negative 3/7. That's the second row. Just copy it down. Now we take negative 5 to the second row and add to the first row. Negative 3/7. 5/7 plus 19/7. And then negative 5 times that, that's 15/7 minus 1, which is 8/7. That's 0. So it's just negative 5 times this row and add to that one. Negative 3/7, 19/7, 15, 8/7. Good. Okay, so then this is so linear system, augmented matrix, reduced to echelon form. And now that we have a reduced to echelon form, I can write the corresponding linear system to this augmented matrix. And that linear system will have the same solutions as the original one, right? This method is meant to simplify the linear system using matrices. And by simplifying, it has the same solutions, but it's easier to find the solutions to our simplified linear systems, okay? And so this simpler linear system, it'll be easier to find the solutions than the original one, and they'll be the same. Okay, and so this is x1 minus 3/7 x3 plus 19/7 x4 plus 8/7 x5. This is x2 plus 2/7 x3 minus 1/7 x4 minus 3/7 x5, and that's equal to 0. So here's now our corresponding linear system to that augmented matrix. And so the leading variables, right, are the ones that correspond with the leading ones there. So the leading variables are x1 and x2. The other ones are free variables. So x3, x4, and x5 are the ones I should set equal to parameters. So I'm going to set equal to r, s, and t. So these three are now going to be set equal to those corresponding parameters. And so I'm going to rewrite this. I'm going to solve for the leading variable. I'm going to substitute x3, x4, and x5 for r, s, and t respectively. And I'm going to solve for the leading variables x1 and x2. And so what you get is that x1 is equal to 3/7 r minus 19/7 s plus 8/7 t. And x2 is equal to negative 2/7 r plus 1/7 s plus 3/7 t. And so now that's x1 and x2. Okay, so that's x1 and x2, and x3, x4, and x5 are that. I'm going to rewrite that here. x3 is r, x4 is s, and x5 is t. Okay, so x1, x2, x3, x4, x5. So that's the general solution using parametric equations. And so find the general solution is done. Okay. I want to confirm that the row vectors of the coefficient matrix are orthogonal to the solution vectors. Okay, so I have the solution here. So I'm going to carefully erase everything else except what I need to finish this problem. So I'm going to erase this, this, and this, and everything else I'm keeping for a reason. Okay, here's the general solution. This is the original linear system. That's its corresponding augmented matrix. The next goal is to confirm, so we found the general solution already. Now we want to confirm that the coefficient matrix, confirm the row vectors of the coefficient matrix are orthogonal to the solution vectors. Okay? So we want to confirm the row vectors of the coefficient matrix are orthogonal to solution vectors. So actually, if we just look at the coefficient matrix, so I'm going to write that here. It's 1, 5, 1, 2, negative 1. 1, negative 2, negative 1, 3, 2. This is the coefficient matrix to that linear system. So we want to confirm that the row vectors of the coefficient matrix, this is the first row vector, that's the second row vector, right? Coefficient matrix for that linear system, first row, I'm going to call the first row R1, and I'm going to call the second row R2. R1 and R2. I want to show that R1 and R2 are orthogonal to the solution vectors. The solution vectors are from this general solution. And so a solution is of the form where the first component is 3/7 R minus 19/7 S. Hopefully I did this right. Plus 8/7 T, comma, negative 2/7 R plus 1/7 S plus 3/7 T, comma, R, comma, S, comma, T. That would be the form of any solution and every solution to this linear system. The first component, second, third, fourth, and fifth, like just like that. And I'm going to separate them by the parameters. And so it's going to be R times 3/7, comma, 1, comma, 0, comma, 0. Wait, R, comma, negative 2, R times 3/7, negative 2/7, 1, 0, 0, plus S times negative 19/7, comma, 1/7, comma, 0, comma, 1, comma, 0, plus T times 8/7, comma, 3/7, comma, 0, comma, 0, comma, 1. Okay? Good, that's it. Okay, so this is a general solution vector, right? So this is a solution vector. And so we want to show that any solution vector is orthogonal to each of these rows. Okay? So I did extra work. We don't need to do this. Sorry. We can just stick with this. This is our solution vector. And so all you have to do is you want to show it's orthogonal to, right? These two row vectors are orthogonal to all of these. And so just take the dot product and find it 0. So we're going to take this vector 1, 5, 1, 2, negative 1 and dot it with that 3/7 R minus 19/7 S plus 8/7 T, comma, negative 2/7 R plus 1/7 S plus 3/7 T, comma, R, comma, S, comma, T. So I'm going to dot product these two, and hopefully I didn't make a mistake anywhere. And this comes out to 0. Okay, and so 1 times this is 3/7 R minus 19/7 S plus 8/7 T plus 5 times this, which is minus 10/7 R plus 5/7 S plus 15/7 T plus R plus 2S minus T. So if we add up the R's, we have 3/7 R's minus 10/7 R's plus R. And so that will be 3/7 R minus 10/7 R, which is negative R plus R, which is 0 R. So that's 0 R plus negative 19/7 S plus 5/7 S, which is negative 14/7 S, which is negative 2S plus 2S, which is 0 S. And then plus 8/7 T plus 15/7 T, which is 23/7. Wait. So for this, the S, no, for the T, this should be a minus here. Okay, so here, I think I made just, this should be a minus sign here. That should be a minus, which means this is a minus, which means this is a minus. That's what I think it'll turn out to. And then there's a minus there. And then if you go back and change things so the answer is right, you then get negative 8/7 t plus 5/7 t, which is 1t minus 1t, which is 0. And so what you should get is that this is 0t, and so it's 0. And I have a hunch that probably should have been a minus sign there. Okay, so you should get minus because you take this and you dot product it with the first row. Now when you take this and dot product with R2, you also get 0. Okay? Okay, let's keep going. Okay, so for 3.5, we have number 8, and then use a, okay, so for number 8, we're going to let the u vector u. V is equal to the vector 2 comma negative 1 comma 2. Good. Okay, so we're going to use the cross product to find a vector orthogonal to both u and v. Okay, so if you find the cross product of two vectors, it's orthogonal to both of those vectors, right? If you have a vector u and you have a vector v, when you take their cross product, you get another vector u cross v, which is orthogonal to both of those original vectors. And so that's what we're going to do. We're just going to find u cross v, and it's going to be orthogonal to both of those. It's equal to the determinant of this matrix, where the second row are the coordinates of u, and the third row is the coordinates of v. So the first row is ijk, the second row are the coordinates of u, and the third row is the coordinates of v. You take the determinant of that vector, of that matrix, and so what you get is you get this. Okay, so then we go there. And so you compute these determinants by multiplying like that. So it's 2 minus 2, which is 0, comma 2 minus negative 4, which is 6, and then negative that, which is negative 6. And then negative 1 minus 2, which is negative 3. You get that vector. 6, negative 6, good. Negative 1 minus 2. Okay, so then u cross v is this vector, 0, comma negative 6, comma negative 3. Okay, so that's u cross v, and that vector is orthogonal to both u and v. So that's number 8. Okay, so that vector is orthogonal to both u and v. Okay, and then number 12. Okay, so in this exercise number 12, 3.5, we're going to find the area of the parallelogram with those vertices. So let's just draw the picture of it. X-axis, y-axis, and so you have 3, 2 here. That's P1. You have P2, which is 5, 4. And you have P3, which is sorry. Let me move the picture because I'm going to start the picture like this. There's not going to be any negative sides of the real axis because we're not using negative numbers. 3, so okay, I'm going to draw this again. 3, 2 is there. That's P1. P2 is 5, 4. Nine, 4, and then P4 is 7, 2. Okay, and so P4 there is 7, 2. And so those are the vertices, P1, P2, P3, 4. So I'm going to draw that, right? That is the parallelogram with those vertices P1, P2, P3, P4. So we're going to find the area of that parallelogram by thinking of the vectors P1, P2, and P1, P4. This is P1, P2, and this is P1, P4, right? So all this is, you watch the online videos and I go into detail about all of this, how to do all this, and so this is now the problem. Okay, so this is P1, P2, and this is P1, P4. And so the area, which I'm going to call capital A is the area of this parallelogram. So this is the area of the parallelogram, so this area of the parallelogram determined by P1, P2, P3, P4. So there's only one parallelogram with those 4 points, obviously. And so this is the area of that parallelogram. And so A is equal to the norm of, I'm going to call the vector U P1, P2, and the vector V P1, P4. And so the area of this parallelogram is the norm of U cross V. Okay, U is the vector P1, P2, V is the vector P1, P4. They're adjacent vectors, adjacent sides to this parallelogram with the same initial point. They both start at the point P1, and they're the vectors that make up the 2 adjacent sides of this parallelogram. And so the norm of their cross product is the area of that parallelogram. And so the area, the norm of the length of U cross V, you could just find U cross V and then determine its length. Okay? So let's find U cross V. So U cross V is equal to the determinant of, first row is I, J, K. The second row are the coordinates of P1, P2. So over here I'm going to write what P1, P2 is. P1, P2 is the point P2 minus the point P1. And so that's equal to 2, 2. Right, P2, the vector P1, P2 is the coordinates of point P2 minus point P1. So that's 2, 2. And P1, P4 is equal to the point P4 minus the point P1. And if you take the corresponding components and subtract them, 7 minus 3 is 4. And then 2 minus 2 is 0. And so P1, P4 is 4, 0. So U, which is P1, P2, is 2, 2. And V is 4, 0. Oh, okay, sorry. So U cross V, we're taking the cross product of 2 tuples. Okay, and so actually let me add this additional point to make. We can find the cross product of 3 tuples from our earlier formula. You can, for 2 tuples, we have a formula for the cross product of 3 tuples. We can make these 3 tuples by adding a z component. So I'm going to make U 2, 2, 0, and I'm going to make V 4, 0, 0. So now I'm going to turn U and V into 3 tuples, even though they're technically 2 tuples, by just adding a 0 in the third component. Okay? They're the same vectors in 2 space, but just with a 0 in the third component, because they have no height. So if you're looking at the x, y axis on the floor, and then the z axis is up, you can think of the vectors in 2 space on the floor as being vectors in 3 space with no height, or a third component of 0. And so let's take the cross product of these three tuples, which are technically supposed to be two tuples. And so we get I, J, K. And we have 2, 2, 0, 4, 0, 0. Okay, and then so then if you find that determinant, you get 2, comma 0, comma 0 minus 8. 2, comma 0, comma negative 8. Okay? Wait. No, sorry, wait. This is 0. Fix this. 0, 0, negative 8. That's what it is. 0, 0, negative 8. Okay? So u cross v is 0, 0, negative 8, and as a vector in 3 space. And so if you take the norm of u cross v, it's the norm of that vector 0, comma 0, comma negative 8, and it's the square root of the sum of the squares of that vector, so 0 squared plus 0 squared plus negative 8 squared, which is the square root of 64, which is 8. So the length of that vector is 8. So the norm of u cross v is 8, and so the answer is that the area of that parallelogram is 8. Okay, so you find the norm of u cross v, but because we're in 2 space, we only have 2 axes here. You can think of the vectors u and v as being 3 tuples by adding a third component of 0 to them. U was originally 2, comma 2, and v was originally 4, comma 0. Just make the third component 0, and now you can take the cross product and you can pretend that they're 3 tuples to find the cross product, and it's the same. Okay, and then you find the cross product, which is that, and you find its norm, and it's 8. Okay, which makes sense, right? If the u cross v is the vector 0, 0, negative 8. You move 0 along the x-axis, 0 along the y-axis, and you move 8 in the negative direction on the z-axis. And so what length is that vector? It's 8, positive 8. Okay, and that's the area. Okay, so that's number 8 in 3.5, and then number 12. Okay, so then so 3.5, I think I already answered that problem. Okay, I already answered it. Right, I did that. Okay. I did number 12. That was 12. Okay, so then we're going to go to chapter 4. And we're going to go to 4.1. So now we're going to go to 4.1, and we're going to go this is now section 4.1, number 7 and 9. Okay, so for number 7 and 4.1, okay, so we want to identify whether or not this is a vector space. Is this a vector space? Which I'm going to abbreviate as is vector space. But you have the book in front of you and you can read the whole question, right? So is this a vector space? And we're looking at the set of all triples of real numbers with the standard vector addition, but with scalar multiplication defined by k of x, y, z is equal to k squared x, comma, k squared y, comma, k squared z. So this is scalar multiplication. Regular scalar addition. Regular addition, I should say, not scalar addition. Regular addition. And the set is R3. So our vector space is R3 along with regular addition along with this new scalar multiplication. Right? A vector space consists of a team of 3 things: a set, an operation of addition, and an operation of scalar multiplication. And if 10 rules hold, then then that team is considered a vector space, right? 10 rules, right? And so in order for this to be a vector space, all 10 rules have to hold. If it's not a vector space, then at least one of the 10 rules is false. Okay? Here's one. One of the rules says that k times u plus v is equal to ku plus kv. Actually, this will hold. Let's see why. So here, this k times this vector, if we let u equal to the vector x, y, z, and we let v be the vector x prime, y prime, z prime, then k times u prime plus v prime is equal to k times x, k times u plus v is equal to k times x plus x prime, comma, y plus y prime, comma, z plus z prime. This is u plus v is this vector, meaning the components of u and v. And so k times this is going to be k squared times each component, equals to k squared times x plus x prime, comma, k squared times y plus y prime, comma, k squared times z plus z prime. And so now you multiply each component by k squared. This is going to equal, after some arithmetic, you can say this equal to k squared x, comma, k squared y, comma, k squared z, plus k squared x prime, comma, k squared y prime, comma, k squared z prime. And that's equal to ku plus kv. And so you can show that k times u plus v is equal to ku plus kv. And so this rule actually holds. Okay? And so this is one of the 10 rules from earlier. I'm going to quickly put it on me so I can help you here. Easier. So this is rule 7. And so number 7 holds. Not number 7, not problem number 7, but axiom number 7. So the 7th axiom holds. So here, okay, so axiom 7 holds. Now that I'm thinking about this, I see something that could go wrong with this being a vector space. In rule number 5, axiom number 5 for vector space, for each u in a vector space capital V, there is some object, some negative u in V, such that u plus negative u equals negative u plus u is equal to 0. And so negative u is equal to negative 1 times u. Okay? But what is negative 1 times u now? Scalar multiplication says you square the number that you multiply by. So negative 1u is now you take the square of negative 1 and you multiply each component by it. And so negative 1u is you take each component of u and you multiply it by negative 1 squared instead of negative 1. And so this is x, y, z. This is u. So negative u, instead of scalar multiplication being multiplying every component by that number, you're multiplying each component by the square of that number. And if you have to multiply each component by the square of a number, you can't get a negative. You can't multiply each component by a negative number, because when you square a real number, you're going to get 0 or a positive number, right? And so this negative u, which is negative 1u, is actually u itself. And so negative u is u, right? And so if u is non-zero, then if I were to take u plus negative u, and I found that negative u is u, whenever I take u plus negative u, I would have to get u plus u, which is 2u, and that does not equal 0. So if u is non-zero, then rule 5 says there's some negative to that vector. I can add to it and get 0. U plus negative u is 0. But I showed that with this new scalar multiplication, negative u is equal to u. And that means that whatever negative u I add to u has to be u itself. And so u plus negative u is now u plus u, which is 2u, but u is non-zero. And so now there is no negative for every vector in this potential vector space, right? A vector does not have a negative with this scalar multiplication, because multiplying by a scalar is multiplying each component by its square. And so I cannot take the negative of each component anymore. Okay? And so rule 5 fails. And so is this a vector space? The answer is no. And it's because rule number 5 fails. Okay, at first I thought it might be 6 through 10, because 6 through 10 really deals with scalar multiplication. But it turns out that actually the definition of scalar multiplication interferes with the 5th rule, which is still, for the most part, talking about addition, which is counterintuitive. So rule 5 fails. This is not a vector space. Okay? Okay, so number 9. Number 9 in 4.1. So instead of 2 by 2 matrices, so again, we want to show, the question is this a vector space? Question mark. And so we have the set, we have the set of all 2 by 2 matrices of this form. So the set of all 2 by 2 matrices of this form, A0, 0, B. And so do all 10 axioms hold? And this is regular addition, standard addition, and regular or standard scalar multiplication. Okay? So the set of all matrices of this form, comma, this addition and this multiplication. I'm going to call this capital M. So it's going to be all the matrices of that form, comma, regular addition, comma, regular scalar multiplication matrices. Regular addition means, right, if you have A, B, C, D plus E, F, G, H, you just add the components, A plus E, B plus F, C plus G, D plus H. That's regular addition. And scalar multiplication is if you take a matrix A, B, C, D, then you multiply it by K. The scalar multiple K, you multiply each component by K. So that's scalar multiplication of a matrix, that's regular scalar multiplication of a matrix, that's regular addition of matrices. And so those are the operations, and we have that set of matrices. And so is this a vector space? Does this satisfy all 10 axioms for a vector space? And so, okay, so let's think of our 10 axioms again. So for axiom 1, if you take a vector u here, and you take a vector v here, if you add them, you get another vector in that vector space. Number 1 holds. You take one vector in that vector space plus another vector, you get It's closure under addition. The second rule is commutativity true. If you take two of these matrices of this form, does it equal if you switch the order of the addition? And the answer is yes. The answer is yes, right? Both those matrices equal that matrix. Those two are equal. So that's commutativity. Rule 2 holds. Rule 3. Okay, so if you add this vector and this vector and this vector in this order, it's equal to the same three matrices when you change the order of the addition, and that's also true. Okay? Okay, I put parentheses here and a parentheses here. So that's also true, right? It's true by associativity of addition of real numbers. Okay? So in the first component, you'll get A plus C plus E, and in the first component here, you'll get A plus C in parentheses plus E. They're the same by commutativity of addition of real numbers. So that's equal to that. That's also true. So the first three rules are true. Okay, if you need to pause it and look at that, you can. I'm going to go to rule 4. So now for rule 4, so for okay, so there's 10. So I found a much faster way. There are 10 axioms, and you can prove rule 10 or hold, just like I was doing. The first 3 were true, and that would work. You show the next 7 are also hold, and it's a vector space. I just now thought you can show this as a subspace of all m sub 2, 2. Now I didn't really go. We didn't go into a formal proof of this. M sub 2, I did maybe mention this. M sub 2, 2 is the vector space of 2 by 2 matrices. It's a vector space. This is the vector space of 2 by 2 real matrices. The coefficients are real. Okay? And it has the same operations of regular addition and regular standard addition, standard scalar multiplication. This is potentially a subspace of that. It's still a 2 by 2 matrix of real entries, and it's just a subset of m sub 2, 2. So if it's closed under addition and scalar multiplication, then by theorem, we know it's a subspace of the vector space of 2 by 2 real matrices. So, so if you take two such matrices, if you take two such matrices and you add them, you get another matrix where there's zeros here and here, right? This is another matrix in M. So this is closure under addition. And if you take a scalar multiple of one of these vectors, then you get another vector in where zeros are here, and you have something there and there. And so this set is closed under addition and scalar multiplication of the same operations in the overlying set, the bigger set, m sub 2, 2. So using the same addition and scalar multiplication as this vector space, this subset of m sub 2, 2 is closed under addition and scalar multiplication. That means this is a subspace of a vector space. A subspace of a vector space is a subset which is also a vector space with the same addition and scalar multiplication. So this is a vector space. It's a vector space as a subspace of m sub 2, 2. And we proved subspace was shown as closed under addition and scalar multiplication, the same operations as m sub 2, 2. Okay? Okay. That's number 9. So that's 4.1. And now let's go to 4.2. Okay? So those are 2 problems in 4.1, and now 4.2. And so there's numbers 3 and 9 in 4.2. Good. So 4.2 numbers 3 and 9. So for number 3, we have a naught plus a1x plus a2x squared plus a3x cubed. Okay? And we're going to determine whether or not this is a subspace of P sub 3. And a naught is equal to 0. Okay, so all polynomials of this form where a naught is equal to 0, is this a subspace of P sub 3? So the question is it a subspace of P sub 3? Well, it's going to be similar to the last problem we just did. We're just going to show it's closed, determine whether or not it's closed under addition and scalar multiplication. So if we take one of these, a naught plus a1x plus a2x squared plus a3x cubed, and we add to it another polynomial of the same form, a naught prime plus a1 prime x plus a2 prime x squared plus a3 prime x cubed. If you add them, you get a naught plus a naught prime plus a1 plus a1 prime times x plus a2 prime x squared plus a3 prime x cubed. Now here a naught is equal to 0, and here a naught prime is equal to 0. They're both elements of the same set, right? So a naught plus a naught prime is equal to a naught plus a naught prime is equal to 0 as the sum of two things that are 0. And so this is of the same form as the original one, right? There's x cubed, x squared, x. They have coefficients, and then there's no constant term at 0. And so it's closed under addition. So it's closed under addition. You're using the standard addition of polynomials in P sub n. And then scalar multiplication, k times a naught plus a1x plus a2x squared plus a3x cubed, where a naught is equal to 0, right? And so if you multiply this whole thing by k, you get k a naught plus k a1x plus k a2x squared plus k a3x cubed. Well, a naught is equal to 0, so k a naught is equal to 0. And so this is 0. And so this is still a polynomial of degree 3, at most 3, that has a constant term of 0. And so this is closed under scalar multiplication. Okay, by this I mean scalar multiplication. So this is a subset of P sub 3 that's closed under addition and scalar multiplication. P sub n, for any n, greater than equal to 0, is a vector space. So P sub n is always a vector space for any n greater than or equal to 0. And P sub 3 is a vector space. And this is a subset of P sub 3 closed under addition and scalar multiplication. It's a subspace of P sub 3. It's a vector space. So therefore, it's a vector space as a subspace of the vector space P sub 3. Closed under addition and scalar multiplication. Right? P sub n has standard addition of polynomials and standard scalar multiplication of polynomials, right? Every vector space has a set, operation of addition, and an operation of scalar multiplication. And so P sub n has those two operations, and it's vector space, subspace of vector space itself is vector space. Okay, so that's number 3. And then there's parts B, C, and D, and they're similar. Okay. Okay, so number 9. Okay, so then for number 9 it says which of the following are linear combinations of A, which is this matrix. That's not gonna be fun. B, which is this one, the last one. 2, 3. C, which is equal to 0, 2, 1, 4. Okay, so that's A, B, and C. And so we want to know whether each of these are which of the following are linear combinations of those 3 matrices. So let me do B first, even though it's out of order because it's just easier. I want to show whether or not this matrix is a linear combination of A, B, and C. It's a 0 matrix, 2 by 2. So it's just 0A plus 0B plus 0C. That's so easy that I'm going to do that before. Okay, so this matrix is a linear combination of A, B, and C, where the coefficients are all zeros. So B is. That's good. Okay. Which one would I want to do next here? Let's do A. Let's just do A. So for A, B is a linear combination. For A, it's 6, negative 8, negative 1, negative 8. Okay, and then it's some multiple of A, which is this matrix, plus another multiple C2 times B, which is that matrix, plus another multiple C3 times the third matrix, 0, 2, 1, 4. Okay? And so from this equation, you get 4 linear equations, and you get a linear system, and you find its solution. You find whether it has a solution. So looking at the first components, you get an equation. So you take each of these 3 things I circled and you multiply them by those constants, you add them, and you set equal to 6. So this is 4C1 plus 1C2, which is a C2, plus 0C3, which is 6. There's negative C2 plus 2C3, which is equal to negative 8. We have negative 2C1 plus 2C2 plus C3 is equal to negative 1. And then that's negative 8 here. This is equal to negative 2C1 plus 3C2 plus 4C3. Okay, so now, so we have that linear system, right? So that linear system with 4 equations, 3 unknowns. So we want to find solutions to that linear system. So I'm only going to do part A and B. I'm not going to do part C also. Okay, so for part A, we just want to find whether or not there's solutions C1, C2, C3, that system. If there is, you'd plug them in here, and you'd have this is a linear combination of those 3. Okay, so if this has a solution, at least one, then you would take that solution, the values of C1, C2, and C3 that satisfy every equation in the system, and that would be values for C1, C2, and C3 here, where the matrix equation holds. Where each component, each of the 4 components, the 4 components on this side are equal to the 4 components on that side after you do all the operations on the right side. Okay, so let's see whether or not there's solutions to that system. If there is, then it is a linear combination. If there isn't, it's not. And then we're done. Okay? We'll use the rest of the board for that. So the corresponding augmented matrix is 4, 1, 0, 6, 0, negative 1, 2, negative 8, negative 2, 2, 1, negative 1, negative 2, 3, 4, negative 8. Okay, so that's our augmented matrix corresponding to this linear system. Let's get to reduced echelon form. That's whether or not we have solutions. Okay. All right, I'm going to multiply the first row by 1/4. Second row, I'm going to multiply by negative 1. Okay, so the first row I multiplied by 1/4. The second row I multiplied by negative 1. The third row, I'm going to take 2 times this row and add it to that one. So 1/2. 5 halves. And take 2 and add to that. It's a 1. I'm going to take 2 times this. 2 times 3. That's going to be a 2. Okay, then I'm going to take 2 times this row again, add to that, and get 0, 7 halves, 4, negative 5. Okay, and then I'm going to keep the first 2 rows the same for now. something with that later. And then the first two rows I'm going to keep the same. And now I'm going to take negative 5/2 times this row and add to that one. Okay, so this will be 5, that's 6. And then negative 5/2 times 8 is negative 20. Negative 20 plus 2 is negative 18. So I did negative 5/2 times this row and added it to that one. This is a negative 2 here. And so negative 5/2 times negative 2 is 5. 5 plus 1 is 6. Negative 5/2 times 8 is negative 20. Negative 20 plus 2 is negative 18. And then negative 7/2. Now I'm going to take negative 7/2 times this row and add to that one. It's going to be 0 here. Negative 7/2 times negative 2 is 7. 7 plus 4 is 11. And then negative 7/2 times 8 is negative 28 plus negative 5, which is negative 33. Okay? And so it looks like it's working out well. Okay, so I'm going to multiply the third row by 1/6. Okay, then I'm multiply the third row by 1/6. And then I'm going to take this row and negative 11 times this row and add to that one. And the fourth row is going to be all zeros. So we're good so far. So the fourth row is all zeros we don't care about anymore. And then I'm going to, actually, I guess I'm going to keep this for now, till the end. Keep writing zeros until the end. And then, just make this perfect. Okay, and then this row is going to stay, I'm going to take 2 times this row and add to that one. And I'm going to take, after I do that, I'm going to take negative 1/4 times this row and add to that one. So I'm doing Gauss-Jordan elimination. Okay, and then negative 1/4, negative 1/4. So negative 1/4. Okay, so negative 1/4, negative 1/4, negative 1/2 plus 3/2 is 1. Okay. And so the result is the fourth row doesn't matter, and we get that C1 is equal to 1, C2 is equal to 2, and C3 is equal to negative 3. Okay? Because that's this corresponds with C1, that corresponds with C2, and that corresponds with C3. And then we get a nice solution here. If you plug those in to your original equation, you can show that the matrix is equal to 1 times A plus 2 times B minus 3 or plus negative 3 times C. That's what the original matrix is. Okay? And then, so that's good for number 9 in this section. Okay, so we went through all the homework problems on the sheet from 3.1 to 3.5 and then 4.1 to 4.2. Okay, so for all 7 sections, I went through each problem in each section. Okay, so I hope this helped. If you have questions, you can email me. And don't forget about the test and watching all the videos and studying. Okay? See you soon. Bye.